proceed. So let's suppose everything was okay. I received also many questions on the process payload part. So assuming some vaults went well, or all of them, you can look at, for example, multi-deposit. This is another instance where something can fail, right? So we have this try-catch in a loop, and it can fail because you can have an underlying vault where the deposit function always reverts, or somebody upgraded the underlying vault to a different implementation, which screws everything up, and this reverts here, going into the catch statement, so it impedes the deposit. And even if the Superform implementation itself, imagine if a new implementation got added to the protocol, which has a bug in this cross-chain deposit into vault function, then it would also go into the catch statement. So it happens as a way to detect if this behavior here is correct. And if it is not, we also push to failed deposits mapping each of the Superform IDs and that are deemed to be failing. So this is the next instance of where failed deposits can be updated. If everything went well, so if this fulfillment is true, and this is true for at least one of the vaults worked in here, if at least one of the try catches in the for loop passed correctly, then an acknowledgement will be sent back to source. An acknowledgement is, it has this return callback type. That's how we identify an acknowledgement. Yeah, this multi-return data shows that the AMB message now is built with return multi-data here. And this is the instance where we submit the message back to source. If none of the vaults worked in the for loop try catch, well, we wouldn't even issue this acknowledgement. The process would just stop there. If all deposits failed, then we wouldn't submit an acknowledgement back. And if we did submit acknowledgement back, then you can check here that these are the original set of AMB IDs. Remember when I was talking about the dispatch? The dispatch payload function. These are the original ones. So the message is brought back, it's received in core state registry, and finally, process payload must be called again by this keeper, but this time, because it's a return callback type for the deposit case, so it's not a fail case for withdrawals, then that's how superpositions are minted one-to-one to the number of vault shares that got minted to the Superform. So that completes the deposit lifecycle. And let me just show you the withdrawal lifecycle real quick, and we can focus on destination swapper a bit, which is also important. If anyone has questions up until this point, feel free to write them down or just interrupt me, no problem. So yeah, the cross-chain single vault withdrawal, similar flow, except we burn superpositions optimistically here. So we're assuming that the withdrawals will succeed, that nothing will fail on destination. And it's good because this way the user cannot use these superpositions for something else. So they're burned right here. The message is sent, this time with a transaction type withdrawal. Notice there's no bridging action here. We're not submitting any liquidity. and the withdrawal flow is simpler. We don't need to update amounts, but we may need to update TX data. And this can happen if the TX data is empty. So the user is able to, if we check the data types here, let's go to the request. This TX data here, this can be empty, and it signals that it should be updated on destination. In most cases, it should be updated on destination, because by the time this TX data reaches the destination, it could have expired. So like the routes, all the parameters needed for any swap or bridge in the destination post withdrawal, they may expire. And that's why there is this option to update the withdrawal payload for each vault with fresh TX data just before processing the withdrawal payload and extract the funds. So that's why this, yeah.
Sorry to interrupt, but I just wondering, in case the user made in exchange withdrawal and he want to take just the underlying asset without any swap, without anything, why update TX data?
No, yeah, in that case it's not updated. So there's a way to signal whether the user is going to do a swap or bridge, or it just wants to receive the collateral. And for the case he wants to receive the collateral, this function is not called.
Oh, yeah, thank you.
So it's optional. The user signals their intention by the way they construct this leak request, and the keeper operates accordingly to the user's intent. And yes, so we can actually briefly look into that for the people that are wondering where this is happening. This is in process exchange withdrawal here. So you see len different than 0, and this pertains to an existing TX data. So if this is null, it means it doesn't update it. So there's no bridging. There's no bridging and swap. The user just receives the collateral. Yeah. So assuming this happened or didn't happen, we go into process payload. And similar case, we have try-catch. So withdrawals can also fail by the same reasons. Vaults are not operational. There's something wrong with the implementation. And you can think whatever comes to your mind. Something can happen here, and we catch those errors. So if errors is true, notice that for the ones that pass, we mark multi-vault data amounts as 0. This means that these indexes here are good. They don't require a remint of shares. But for the indexes that failed, we keep these amounts as they are. So we don't update with 0. And this is to signal back on source which indexes have to have their superpositions reminted to the user. So if there's at least one vault in the multi-vault case where there are errors, we return an acknowledgement. For the other cases where all the vaults pass, there's no acknowledgement, the withdrawal finishes. But if there's at least one error, similar thing as the deposit, we build this return data, and the message is sent via the INB bridges. It reaches core state registry on source. Process payload is called, and this time the callback type will be fail. And we reissue superpositions by calling state sync or state multisync. So that's how we cover for the original superpositions that were optimistically burned. So we remit them back to the user in that case. Cool. Cool. So we didn't see one case in deposit, which is more complex cases where in certain destinations there's not enough liquidity for the token that the vault required, the vault collateral. So there must be a swap from a higher liquidity token to that lower liquidity token. And typically that higher liquidity token it's the token that got bridged. So that happens in destination swapper. So when a destination swap is needed, that is obviously signaled to the keeper. The funds that are bridged, they don't reach core state registry. They reach the destination swapper first. And this is where that processing and swap happens. And there's also a slippage check here, different than that update deposit one. So there's a chance, let's jump into the internal process ticks. There's a chance that this reverts, that this is outside of the slippage bounds. And in this case, this also configures a failed deposit. Okay, so for this process, a keeper is allowed to call this function update failed tx. There's an equivalent batch one, and here you can look into it. Of course, we verify that the user's intent is correct against what the keeper is proposing to rescue. This function basically signals what is the token and what is the amount that is going to be rescued, the amount that got stuck here in destination swapper. So there's a variety of checks, including if the token has balance according if it's native or not. Just some sanity checks for this rescue to happen. So this failed swap, core state registry will have access to this, and the rescuing does not happen here. So this is just signaling what is the interim token and what is the amount. The actual rescuing happens through core state registry as well. So failed deposits, yeah. So this failed swap will be obtained in core state registry. Where? So a keeper must go then, after calling update failed tx, must call update deposit payload for this particular payload that failed. And what we can see here is a different behavior. So in the case where there are destination swaps, we get this swapped amount. So that's the first thing that happens here. And in case where this is different, because if this reverts, this is 0. No swapped amount happens. So this is going to be different than final amount. Thus we can graph the amounts that the keeper updated in failed swap mapping, the amount, and the interim token. By this point, we know that that the action failed on destination swapper, but we must still do a sanity check that this amount updated here matches the proposed final amount. So the keeper must submit the final amount equal to the other value that another keeper updated here. Otherwise, we revert here. And if successful, similar cases as for the simple failure and core state registry, we also update failed deposits, Superform IDs, the interim token in this case, and also turn this flag into true. That this is going to be treated differently. And this time failed swap queued is true. So no need to enter in this if statement and do this process. That was for the first instance. So this is the third instance where failed deposits is updated. and similar process goes with the propose, dispute, finalize, except that this time, since the settle from destination swapper is true, we're not going to send from core state registry. We're going to send, like I said, the funds are trapped in destination swapper. We're going to call process failed TX. Core state registry will call via the keeper, and the funds are extracted through here. Only core state registry can call it. And this is where the transfer to the refund address happens. That sums the failed cases for deposits, also shows the cross-chain behavior. Really simplistic for deposits and withdrawals. You could go deeper in some areas. Any questions up until now? Anything? Could you give some advices for participants who are currently entering competition? What key areas they should focus on initially? What are important considerations they should they keep in mind? So the first thing to know is that vendor folder is out of scope. That's something you should know. Past findings as well. And in terms of areas to focus, so the critical invariant of our protocol is that the superpositions that are minted are equivalent to the vault shares. So that there's a one-to-one relationship between superpositions and vault shares. If by some means anyone is able to mint more superpositions than they should, then this breaks the invariant, and that's very critical problem to the protocol. So that's ensuring that this invariant always remains. It's very important. The slippage checks, ensuring that this failed flow is operating well. That's another good key area of focus. As you've noticed, the failed deposits process is quite complex. There are 3 distinct areas where it can fail, or where we're adding things to the failed deposits. And I think each one of these areas should be evaluated carefully. Could be a key area to focus, and that we must ensure it's really working smoothly. Perhaps another key area is the whole function of the AMBs. And basically, if our whole idea with message proof and how the quorum behaves. By the way, I didn't talk about the quorum, but something you can also focus is this quorum checks here. So there's a quorum check in every action, and there are chances where a certain message may not arrive, or a certain proof may not arrive. Maybe the AMB got stuck, something like that. So is the protocol covering well for that? Do we have enough ways to ensure that the payload does not get stuck forever? That we can still process this transaction. That's also an area of possible focus. Think about failures in the actual AMBs and what can happen to us, and specifically about the quorum. So this get quorum check, and notice that's another hint that I'm giving to you, that where is the quorum? Utils quorum manager, and try to think a bit also about this set required messaging quorum, which is used here in Super Registry. This is influenced by protocol admin, but in theory, this can be overridden. So you can also check that this behavior is good and matching our intended usage of behaviors. There's also the docs. So we just released a simple explanation of these flows in our docs. So if you consult docs.superform.xiz, I'm just sending the link here. You have a section called end-to-end flows. And maybe I'll share the screen there. So maybe I see now my Safari window. Yeah, so this gives you an overview of this same chain, cross-chain deposit, same chain withdrawal, cross-chain withdrawal flows. I would start by reading this if you're just entering the audit now. Gives you a good overview of what I explained for cross-chain and also for same chain. If you're more curious, dive in on the other areas. I think the diagrams are also a good help. So yeah, these things I said about the focus and key areas and reading this should give you a good start.